Okay, some standard definitions then. So a standard definition, a standard way of working, which is a fair way of working. So everybody's singing from the same hymn sheet, doing the same thing. The standard enthalpy of combustion. So this is when you're measuring something that's burning. So if I wanted to work out the heat change, how good a fuel is, how much heat is given out by petrol compared to diesel, when diesel burns, compared to wood when wood burns, or when ethanol burns, I need to have a fair test. So I need the same amounts of each, otherwise it's not fair. So if we're going to work out, say for example, that petrol is the best fuel, I need the same amounts of petrol, diesel, wood, ethanol, wax, candle wax, whatever I'm burning. And that amount is 1 mole. So it's the enthalpy change, the heat change, how much heat is given out, because combustion always gives out heat, it's always an exothermic reaction, when 1 mole of a substance is burned completely. It's no good just burning part of it or partially burning it, it's got to be burned completely. In oxygen, with all the reactions and products in their standard states. Standard states is how you'd find them in the laboratory. So what condition they'd be in at room temperature, which is 25 degrees C or 298 Kelvin, and standard room pressure, which is 100 kilopascals, or in old units, 1 atmosphere. Okay. The standard enthalpy of formation. Formation is to make something. Okay, so if you bake a cake, you're making a cake. Okay, that's the enthalpy change. So the amount of heat that's given out when you make something, enthalpy of formation, is again to make 1 mole of something. A compound is where you've combined some atoms when you've made them and combined them together. So when 1 mole of a compound is formed, made, again from their elements in their standard states. So if I wanted to make magnesium oxide and measure the heat change when I make magnesium oxide, I'd need to make 1 mole of magnesium oxide. From magnesium and oxygen, how I would find them in the laboratory. Now, magnesium's a shiny metal under room temperature and pressure, and oxygen's a gas. So I'd be reacting magnesium and oxygen gas, magnesium metal, a solid, oxygen gas, a gas at room temperature and pressure, and I'd be making 1 mole of magnesium oxide. Enthalpy of formation of an element. Let's say I was making oxygen, or making silver, or making gold, or making nitrogen. They're all elements. An element is something where all the atoms are the same. Well, I can't make an element. I make something by combining different atoms together and bonding them together to make something new. A compound, different atoms bonded together. An element are all the same atom. I find an element in the environment. I can go panning for gold and find gold in a stream. Similarly for silver, silver in a rock. Oxygen, nitrogen from the air. So I don't make elements because I'm not combining different atoms together and bonding different atoms together to make something new. So the enthalpy of formation of an element is 0 because you don't actually form it, you just find it. Some reactions are difficult to measure. We say they're not feasible, it's not possible. Or some reactions just are difficult to do. So say for example, if I burn carbon from coal, carbon in oxygen, and I burn it, I make carbon monoxide if there's not enough oxygen there. Okay, so I have to limit the amount of oxygen. Otherwise, if there's more oxygen there, instead of incomplete combustion to make carbon monoxide, it would completely combust, completely burn and make carbon dioxide. So it's very difficult to make carbon monoxide. You'd have to limit the amount of oxygen that goes in there. That happens in a car engine or a faulty gas boiler, something like that. So most of the time, carbon would burn with a plentiful supply of oxygen, and it would be complete combustion and make carbon dioxide. So it's very difficult to make carbon monoxide and limit the amount of oxygen unless, as I say, you've got a car engine or you've got a faulty gas boiler, something like that. That's a difficult reaction to do. Other reactions aren't feasible. If I have some copper sulfate, which is white when it's dry, got no water in it, and I add water, okay, it dissolves. It actually makes a solution, a blue solution. Now, if I evaporate the water evaporates, some of it evaporates, and some of it goes into the copper sulfate and forms something called crystals, which is CuSO4.5H2O, which means that it's a crystal. But it's difficult to do that in one step. You have to put the copper sulfate in the water, it dissolves to make a blue solution. Then you leave it on the windowsill to evaporate. The water evaporates and some of it goes into the crystals and it makes blue crystals, copper sulfate CuSO4.5H2O. But you can't do it in one step, because when the copper sulfate goes in the water, it first of all dissolves. It doesn't make crystals straight away. So some reactions are not possible. That is not a feasible reaction. You need to do it in 2 steps. Okay. Finally, some A-level questions say, how do you know when a reaction is over? How do you know when it's complete? Because if I'm talking about standard enthalpy of combustion, I'm saying when a substance is completely burned, completely reacted. Well, the best way to say if a reaction is complete is you carry on taking readings until there is no further change. Okay. So say, for example, I put chalk in acid, calcium carbonate, the proper word for chalk, in acid, it reacts and it makes bubbles of carbon dioxide. Those bubbles of carbon dioxide escape into the atmosphere, okay, and I can see it bubbling. If I wanted to know when that reaction was over, I could either carry on looking at it and decide when the bubbles had stopped, that's fine, no further change, the bubbles have stopped coming. Or I could put it on a top pan balance, and even gases like carbon dioxide weigh something, they have some mass. So as the gas escaped into the atmosphere, the mass of the contents of the beaker would be going down and down and down and down and down. So I'd wait until the mass no longer went down anymore, because all the carbon dioxide had escaped, or just observe it very carefully until it stopped bubbling. But that's how you know if a reaction is complete, because you carry on taking readings or observations of the bubbles or the mass of the beaker or whatever until it no longer changes.